Hi everyone. Note 6.3 are on investigating exponential relationships. So it says the temperature collected by a temperature probe has been recorded in the following table right here. So we have this table, and then we also have a graph for it, okay? So let's just add the letter H here. There's a typo. It has been recorded in the following table. So question A says to first calculate our first differences. So remember, to find our first differences, we just subtract each corresponding y value. So our first difference here is 4. Our next one is 18 minus 6, and 18 minus 6 is 12. And then the next one right here that we have is 54 minus 18, and when we do that, we end up getting 36 right here, okay? For the next one right here, we'll do some calculating. So I'm going to take 162, and I'm going to subtract 54, and I end up getting 108. Okay, and then we'll keep going with this right here. So we'll do our last one right here, 486 minus 162, and we get 324. Okay, now part B says to calculate the second differences. So our second differences that we have here, same thing, I'm just going to take the first differences of the first differences here. So to calculate my second differences, I'm going to take this 12 and subtract 4, and I get 8. I'm going to take the 36 and subtract 12, and I get 24. Okay, here I'm going to take 108, and I'm going to subtract 36, and I will get 72. Okay, let's just double check. 108 minus 36 gives me 72. Good. And then our last one, 324 minus 108, will give us 216. Okay. So by looking at this right here, our first differences are not constant, so it is not linear. Okay, and we should know that if our first differences aren't constant, then it's not linear. Okay, our second differences are also not constant, so it is not quadratic. Okay, so let's take a look at what we have here. Part C says calculate the ratio of successive y values, and to find the ratio, we just divide y2 by y1. So let's talk about how we can do this right here. So here, this is y2. I'm going to divide it by y1. So 6 divided by 2, and I get 3. Okay? For the next one, I'm going to take 18 and divide that by 6. And when I do that, I also get 3. For the next one, I'm going to divide 54 by 18. And when I divide that, I also get 3. When I do the next one, I'm going to take 162 and divide that by 54. So 162 divided by 54, and I still get 3. And then for my last one here, I'm going to take 486 and divide that by 162. And when I do that, I still get 3. Okay? So what this is going to tell us is this is exponential. And remember, exponential means you've got an exponent, okay? So this should make sense because when you have an exponent, it means you're repeatedly multiplying. So here we are repeatedly multiplying by 3. And we know that from our ratio of successive y values, okay? So if you notice, it says to plot the xy coordinates and draw the graph. So if you see right here, at 0 it's 2, at 1 it's at 6, at 2 it's 18, so on and so forth. And my graph is starting off pretty slowly, and then all of a sudden it just shoots way up. And that's what happens when you have exponential growth, because what's happening is it's starting normally, and then the more you multiply by a number, the larger your number gets. It gets bigger and bigger, like super fast, okay? So in an exponential relation, For equal steps of x, neither the first nor the second differences are constant, because then we would have either linear or quadratic, but the ratio of the consecutive y values are constant. Okay, and just a reminder, to find the ratio, you need to divide. All right, so the graph will increase, the graph increases rapidly as you move to the right on the x-axis, and then what's going to happen is it's trying to approach like a vertical line right here. So it approaches a vertical line, okay? This is an example of exponential growth because it's getting bigger, okay? So let's go ahead and talk about some terminology here. So exponential growth right here is just nonlinear growth. So it's not a line represented by an exponential relation and a graph with a rapidly increasing upward curve. So exponential growth is going to look like this right here, okay? And an example of a real-life scenario that would use exponential growth is populations, right? So like, for example, Shelburne, for example, there's been a lot of growth in Shelburne recently, and we could possibly classify that as exponential growth. Or if you just look at a population of animals, if you start off with just a couple animals, the more they reproduce, the more animals there are, and then more animals are reproducing, and it just gets larger and larger and larger, okay? And then exponential decay is nonlinear still growth represented by an exponential relation and a graph with a rapidly decreasing downward curve. So what exponential decay looks like is more like this, where it's eventually going to level off. Okay, so an example of that would be like something boiling and then it cools down to room temperature. Or we could have an example where you have medicine in your system, like you take a Tylenol, for example, and it's effective at first, but then eventually every little bit you've got less and less effectiveness in your system because there's less and less of it actually in your system. Okay? All right, so let's go ahead and take a look at what we have right here. So an exponential function is a function with a variable in the exponent. So for example, right here, y equals a to the power of x, this is the general form. So right here, this a is always going to be your base, and it's always going to be a number, and your x right here is the actual variable. Okay, so some examples would be y equals 2 to the power of x, and what this means is you are repeatedly multiplying by 2. Here, your base is 10, so it's y equals 10 to the power of x. You're repeatedly multiplying by 10. Here, you're repeatedly multiplying by 2/3. And if you notice, the x is always going to be in the exponent right here. Okay, so let's take a look at what we have for question number 1. It says, sketch the graphs of y equals 2 to the power of x and y equals 3 to the power of x on the same axes. So I'm going to color code this. So I'm going to do each one in a different color so I can see what's happening here. And so for the first one, if x is -3, I'm going to do 2 to the power of -3. And we learned in our last video that a negative exponent is just going to flip our value here, so it becomes 1 over 2 to the power of 3, and 2 to the power of 3 means 2 times 2 times 2, which will get 8, because 2 times 2 is 4, and 4 times 2 is 8. So I get 1/8 right here, okay? For our next one, it's 2 to the power of -2, so I'm going to flip it, and I get 1 over 2 to the power of +2, and 2 to the power of +2 is just 4, okay? For the next one, it's 2 to the power of -1. So I flip it, I get 2 to the power of +1, so I get 1 over 2 right here. Okay. The next one, we get 2 to the power of 0, and if you remember from our last notes, anything to the power of 0 is always 1, so I get 1 here. Okay. For the next one, it's 2 to the power of 1, so it's literally just 2 multiplied by itself one time, so my answer is 2. I don't need to do any flipping because my exponent is positive. Next one is 2 to the power of 2, and 2 to the power of 2 means 2 times 2, which is 4. And then the last one is 2 to the power of 3, which is 2 times 2 times 2, which we figured out is 8. Okay? All right, so I want to go ahead and graph this out right here. So what I'm going to do is I'm going to label this my x-axis, label this my y-axis. I'm going to go by ones, so 1, 2, 3, 4, 5, 6. I'm not going to label every single one. You can if you want to. And then I'm going to go ahead and graph out my coordinates. So my first coordinate that I have here is -3 and then 1/8. So I'm going to go to -3, and I'm just going to go a tiny bit above 0 because it's a really small number. It's a fraction. It's 1/8. Okay? The next one is -2 1/4. So it's another really small number. I'm going to go a quarter of the way up between 0 and 1. So that's where I'm going to put this here. The next one is -1 1/2. So I'm going to go to -1 and I'm going to go halfway up. Okay. The next one is 0, 1. So I'm going to go to 0 and 1 and plot that out. Then I have 1, 2. So I'm going to go to x equals 1 and y equals 2. Then I've got 2, 4. So I'm going to go to 2 and then up 4 right here. And then my last one is 3, 8. And it's slightly off, but that's okay. We'll just put it right here, 3, 8. And if you notice, it starts really small, but it keeps getting bigger and bigger. The next one, I'm going to do 8 times 2, so I'll get 16, so I'll get even higher. So this is what my graph is going to look like. And it's never going to go below the x-axis if it's in this format right here. Okay? So this right here is y equals 2 to the power of x. All right, so now let's do the same thing for 3 to the power of x. Okay, so it's the same idea, but this time 3 is going to be our base instead of 2. So here I'm going to do 3 to the power of -3. So when I do that, again, negative exponent means I flip it. So I get 3 to the power of +3, and 3 times 3 times 3 means 3 times 3 is 9, 9 times 3 is 27. So I get 1 over 27 right here. Okay, for the next one, it would be 3 to the power of -2, so I get 1 over 3 to the power of +2, so I get 1 over 9. Okay, next one is 3 to the power of -1, so I get 1 over 3 to the power of +1, so I get 1 over 3. Next one is 3 to the power of 0, and anything to the power of 0 is always 1. The one after that is 3 to the power of +1. I don't have to do any flipping because it's a positive exponent, so my answer is just 3. Okay? Then I've got 3 to the power of 2, which means 3 times 3, which is 9. Okay? And then lastly, I've got 3 to the power of 3, which means 3 times 3 times 3, which we already figured out is 27. So let's go ahead and graph this out. So -3 is going to be plotted at 1 over 27, which is even smaller than this 1 over 8. Okay, so it's barely above the x-axis. -2 is at 1/9 right here. -1 is a third of the way through, so I'm going to go a third of the way through right here. And then 0 is at 1, 1 is at 3, and then 2 is going to be at 9. It's a little bit off, but that's okay. And then we don't have room for 3, 27, so this is what our graph is going to look like right here. It's still exponential growth, it's just growing more rapidly because our base is a larger number. So question A says, comparing to the general exponential function, y equals a to the power of x, is a greater than 1, or is a between 0 and 1? So if we look right here, our a values are 2 and 3, so a is greater than 1. And then if I look at the y-intercept, it's the same for both of them. It's 0, 1. And there's no x-intercept because it doesn't cross the x-axis. So there's no x-intercept. And then we're going to say that the functions are increasing because they are going up. Okay, so for number 2, we've got y equals 1/2 to the power of x and 1/3 to the power of x. So we're going to do this one again, same idea, but we just need to be careful about the fact that we have fractions here. So here I'm going to do 1/2 to the power of -3, but that -3 tells me to flip this 1/2, so it becomes 2/1, or just 2 to the power of 3, which is 8. Okay, here I have 1/2 to the power of -2. This 1/2 tells me to flip, or sorry, this negative tells me to flip the 1/2 to just 2, and that changes the exponent to a +2, and 2 times 2 is 4. Next one, I've got 1/2 to the power of -1. I have to flip it, so it becomes 2 to the power of +1, which is 2. Next one, I have 1/2 to the power of 0, and anything to the power of 0 is always 1. Okay, and then for this one right here, it's 1/2 to the power of 1, and anything to the power of 1 is just itself. Here, it's 1/2 to the power of 2, so that just 1/2 to the power of 2 just means 1/2 times 1/2. 1 times 1 is 1. 2 times 2 is 4, so I get 1/4. And then for this last one, it's 1/2 to the power of 3. So I'm going to do 1/2 times 1/2 times 1/2. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So I get 1/8 here. Okay, so now to graph it, I'm going to put x and y right here. I'm going to put 0 here. I'm going to go by ones, just like we did before. So I'm going to put 3, 6, -6, -3. If this is too fast for you, please feel free to pause and take your time. So our first coordinate is -3, 8. So I'm going to go to -3 and then to +8, and I'm going to put a dot right there. Our next coordinate is -2, 4. So I'm going to go to the left 2 and up 4. Our next coordinate is -1, 2. Our next one is 0, 1. Then we have 1, 1/2. So I'm going to go halfway through. Then we have 2, 1/4, so I'm going to go 1/4 of the way. And then we have 3, 1/8, so I'm going to go 1/8 of the way. And when I connect these dots here, I end up getting my graph looking like this. Okay? This one right here, I would like you to do on your own and have me check it before you work on your problem set to make sure you're good to go. Okay? So for this right here, is the a value bigger than 1 or between 0 and 1? It's between 0 and 1. The y-intercept is still 0, 1. There is no x-intercept, and this time our function is decreasing. Okay? And that's it for the video. Let me know if you have any questions. Have a great day.